Have you ever wondered what happens to the chemicals around us? Where do pollutants go when they enter the air? Why do some rivers turn toxic while others stay clean? And how do human activities change the chemistry of our planet? The answers lie in environmental chemistry, the science that connects chemistry with the world around us. Introduction to Environmental Chemistry, Understanding Chemical Processes in Our Environment. What is environmental chemistry? Environmental chemistry is the study of chemical processes occurring naturally in the environment and how human activities influence those processes. Unlike traditional chemistry, which studies reactions in controlled laboratory settings, environmental chemistry examines complex natural systems. It focuses on the atmosphere, water bodies, soils, and living organisms. This field seeks to answer critical questions. What chemicals are present in the environment? How did they get there? What reactions are they undergoing? And most importantly, what effects do they have on ecosystems and human health? Why environmental chemistry matters. Environmental chemistry plays a crucial role in solving today's environmental challenges. It helps us understand pollution and track how contaminants move and transform in nature. For instance, studying air pollution chemistry explains why smog forms in cities and how sulfur dioxide and nitrogen oxides cause acid rain. In water systems, environmental chemistry determines whether water is safe for drinking and what happens when chemicals enter rivers and lakes. This knowledge supports environmental impact assessments, waste management strategies, climate change research, and the development of sustainable solutions. Simply put, environmental chemistry provides the scientific foundation for protecting our planet. Branches of environmental chemistry. Environmental chemistry is a broad field that connects with several scientific disciplines. Atmospheric chemistry focuses on the composition and reactions in the air, including greenhouse gas behavior, ozone depletion, and photochemical smog formation. Aquatic chemistry studies water systems such as oceans, rivers, lakes, and groundwater, examining parameters like pH, dissolved oxygen, and water hardness. Soil chemistry investigates the chemical composition of soils, nutrient availability, and how substances like pesticides, fertilizers, and heavy metals interact with soil particles. Ecotoxicology integrates chemistry and biology to understand how chemical substances affect organisms and entire ecosystems. These branches work together to provide a complete picture of environmental processes. The Earth's chemical spheres. Understanding environmental chemistry becomes easier when we divide Earth into 4 interconnected chemical spheres. These spheres constantly interact, exchanging energy and matter. The atmosphere. The atmosphere is the layer of gases surrounding Earth. It consists mainly of nitrogen at 78%, oxygen at 21%, and trace gases including carbon dioxide, methane, ozone, and water vapor. Chemical reactions in the atmosphere influence climate, weather patterns, and air quality. Key processes include photochemical oxidation, ozone formation, and greenhouse gas accumulation. The hydrosphere. The hydrosphere includes all forms of water: oceans, rivers, lakes, underground aquifers, and even atmospheric water vapor. Aquatic chemistry helps us understand water properties, the behavior of dissolved substances, and important processes such as eutrophication, mineral dissolution, natural buffering systems, and water contamination pathways. The lithosphere. The lithosphere refers to Earth's solid portion, the rocks, minerals, and soil that form the planet's crust. Soil chemistry focuses on nutrient cycles such as nitrogen and phosphorus, soil pH levels, mineral weathering processes, and how pollutants bind to or move through soils. Understanding soil chemistry is essential for agriculture, proper waste disposal, and maintaining ecosystem health. The biosphere. The biosphere is the zone where life exists, encompassing all plants, animals, microorganisms, and humans. Environmental chemistry investigates how chemicals enter living organisms, how they bioaccumulate in tissues, and how they biomagnify as they move up food chains. This field also explains natural biochemical cycles, including the nitrogen cycle, carbon cycle, and sulfur cycle. Natural vs. human-made chemicals. Chemicals in the environment can be naturally occurring or anthropogenic, meaning human-made. Natural chemicals include nitrogen gas, water, minerals, and organic compounds produced by living organisms. These have been present in ecosystems for millions of years. Human activities, however, introduce many new substances into the environment. These include pesticides, plastics, pharmaceutical residues, industrial effluents, and emissions from burning fossil fuels. Understanding the difference between natural and anthropogenic chemicals helps assess environmental impacts. For example, naturally occurring metals may be harmless in their original forms, but industrial activities can convert them into toxic compounds that accumulate dangerously in ecosystems. Basic chemical principles. Environmental chemistry relies on foundational chemical principles. The periodic table arranges all chemical elements according to their properties. Knowing an element's position on the periodic table helps predict its behavior, reactivity, and environmental role. Chemical bonding is another essential concept. Atoms combine to form molecules through ionic, covalent, or metallic bonds. Understanding bonding explains why some substances dissolve easily in water, why certain gases react in the atmosphere, and how pollutants degrade over time. Chemical reactions drive environmental processes. These include oxidation and reduction reactions, hydrolysis, and photochemical reactions triggered by sunlight. The behavior of chemicals in the environment depends on these reactions and on conditions such as pH, temperature, sunlight exposure, and the presence of catalysts. Human impacts on environmental chemistry. Human activities have significantly altered natural chemical cycles. Burning fossil fuels increases atmospheric carbon dioxide concentrations, driving climate change. Excessive use of nitrogen and phosphorus fertilizers leads to eutrophication in lakes and rivers, creating oxygen-depleted dead zones. Industries release heavy metals and organic pollutants into water and soil systems, contaminating drinking water sources and agricultural land. Understanding these impacts allows environmental scientists to design effective monitoring programs, develop pollution control methods, and create strategies for sustainable resource use. Environmental chemistry therefore serves as a bridge between scientific knowledge and practical solutions to environmental problems. Summary. This lesson introduces the foundation of environmental chemistry by explaining its meaning, importance, and scope. We've explored the four chemical spheres of Earth, the atmosphere, hydrosphere, lithosphere, and biosphere, and examined the basic principles that guide chemical behavior in the environment. Understanding these concepts is essential for grasping more advanced topics such as analytical techniques, pollution chemistry, water quality assessment, and chemical transformation reactions in environmental systems. Closing message. Environmental chemistry is more than just a subject. It's a tool for understanding and protecting our planet. By studying how chemicals behave in nature and how human activities alter these processes, we can develop sustainable solutions for a healthier future. Environmental chemistry, building knowledge for a sustainable world. Thank you for learning with us. Subscribe for more environmental science lessons.